This is a stochastic processes, Module 9, branching processes. In the lecture 1, we have discussed the definition and examples of branching processes. Important discrete type branching process, Galton-Watson process, is discussed in detail. We found mean and variance of Galton-Watson process. Then we find the probability of extinction for the Galton-Watson branching process. This is lecture 2. In this lecture, we are going to discuss Markov branching process. This is a very important branching process of a continuous type. In this, we are going to start with the probability generating function. Then we are finding the probability of extinction, and we discuss the limit theorem. Finally, we are going to discuss some other important branching processes at the end. What is a Markov branching process? Let Zt be the number of particles at time t. The sequence Z of t, the collection of random variables Z of t for t greater than or equal to 0, form a Markov branching process with the following assumptions. Let delta 1 comma k plus ak times h plus order of h, or k is equal to 1, 0, 1, 2 and so on, represents the probability that a single particle will split producing k particles during a small time interval t to t plus h of length h. Delta of 1 comma k denotes the Kronecker delta function. Assume that a1 is less than or equal to 0. For k 0, 2, 3 and so on, ak's are greater than or equal to 0. And summation of ak's starting from 0, 1, 2 and so on, that will be 1, that will be 0. We further postulate that individual particles act independently of each other, always governed by the infinitesimal probabilities. Note that we are also assuming time homogeneity for the transition probabilities, since ak is not a function of time at which the conversion of split occurs. Since ak is not a function of the time at which the split occurs. The similar assumptions we have taken care in the discrete type branching process also. Each particle lives a random length of time following an exponential distribution with the mean 1 by lambda. That is same as A0 plus A2 plus A3 and so on. On the completion of ith lifetime, it produces a random number d of descendant of like particles. The probability mass function of d is probability that d is equal to k will be a suffix k divided by a0 plus a2 plus a3 and so on. The lifetime and the progeny distribution of separate individuals are independent and identically distributed. Using the independent assumptions, we get the conditional probability of zt plus h is equal to n plus k minus 1 given z of t was n. That is same as n times a suffix k of h plus order of h. You know that small order of h means small order of h divided by h tends to 0 as h tends to infinity, as h tends to 0. Order of h divided by h tends to 0 as h tends to 0. And for k equal to 1, the probability of z of t plus h is equal to k given z of t is equal to n. Probability of z of t plus h is equal to n given z of t is equal to n, that will be 1 plus n times a1h plus order of h. So for k 0, 2 and 3 we have a separate expression, and for k equal to 1 we have a different expression. Now using the conditional probability, we are going to define the probability generating function. Now let pi comma j of t is nothing but the conditional probability of a probability of z t plus s is equal to j given z of s was I. Using this, we define the probability generating function, that is nothing but psi of t comma s with the two variables summation over j pij of t s power j. So this will be the probability generating function for pij of t, where pij of t is the transition probabilities. Now we are going to discuss the probability generating function of z of t in the theorem 4. Already first 3 theorems are discussed for the discrete type branching process. So here we are going to discuss the 4th theorem. The probability generating function for pij of t, that is psi of t comma s, satisfies psi of t plus v of comma s, that is same as psi of t comma psi of v comma s. This is a continuous time analog of theorem 1 in the case of discrete time branching processes. We will discuss the proof. Since individual particles act independently, we have the fundamental relation, the probability generating function for pij of t, that is nothing but summation over j, instead of the transition probability I to j, it is a transition probability of 1 to j of t s power j the whole power I. That is same as the probability generating function power I. The reason is the formula means that the population z of t comma I involving in time t from I initial parents is the same probabilistically as the combined sum of I population each with one initial parents. Therefore, the left hand side is the probability generating function for pij of t, that is same as making summation over j the probability transition probability of p1 comma j of t s power j the power I. That is nothing but the probability generating function for pij power I. Also, this formula characterizes and distinguishes branching processes from other continuous time Markov chains. By the time homogeneity, the Chapman-Kolmogorov equations take the form, the one step transition probability of pi comma j t plus v can be written in the form of summation k p I to k of t, then p k to j of v. Because it satisfies the time homogeneity, one can write the Chapman-Kolmogorov equations, because this is a Markov branching process. Now, the probability generating function of the time t plus v, the whole power I, that is same as the summation j pij of t plus v power j. So, using Chapman-Kolmogorov equation, you can write the pij of t plus v is a summation over k pi k of t p kj of v. That is same as summation over k pi k of t summation over j p kj of v s power j. We know that this is nothing but the probability generating function for p kj of v, that is same as the probability generating function of v comma s power k. And this will be written as the probability generating function of psi of t comma psi of v comma s the whole power I. When you substitute I is equal to 1, we get the result, because psi of t plus v comma s is same as psi of t comma psi of v comma s. When you substitute I is equal to 1 in this equation, you will get psi of t plus v comma s is same as psi of t comma psi of v comma s whole power I. When I is equal to 1, you will get psi of t plus v comma s is same as psi of t comma psi of v comma s. Now, we will move into the theorem 5, which discuss the differential equation corresponding to the probability generating function for Pij of t. Let u of s is equal to summation ak s power k summation over k. Then the probability generating function for Pij of t satisfies partial derivative of psi of t comma s with respect to t is equal to partial derivative of psi of t comma s with respect to s multiplied us, and partial derivative of psi of t comma s with respect to t is same as u of psi of t comma s, with the initial condition psi of 0 comma s is same as a summation over j pij of 0 s power j, but that is nothing but s. So, the theorem 5 gives the partial differential equation and the ordinary differential equation satisfied by the probability generating function of Pij of t. Let us see the proof. We start with psi of h of s, psi of h comma s, that is nothing but the summation over j p of I comma j of s, p of I comma j of h s power j. Substitute Pij of h and simplify, you will get the first term will be s, the second term will be h times summation over j aj sj, the second term will be order of h. You know that u of s is same as the summation over j a suffix j of s power j. Therefore, the probability generating function for Pij of h comma s, that is nothing but s plus h u of s plus order of h. We know that by the theorem 4, psi of t plus h comma s will be psi of t comma psi of h of s, h comma s. So, substitute psi of h comma s with s plus h of us plus order of h. Therefore, this will be psi of t comma s plus h of us plus order of h. By Taylor's theorem, we expand the right hand side with respect to the second variable. Therefore, the right hand side will be psi of t comma s. The second term will be partial derivative of psi with respect to s times h of us, h times us plus order of h. All the other term vanishes. Throughout divide by h and take psi of t comma s in the left side. Therefore, the left hand side becomes psi of t plus h comma s minus psi of t comma s divided by h, whereas in the right hand side will be partial derivative of psi with respect to s times u of s order of h divided by h. Taking h tends to 0 positive, we get the partial differential equation dou psi divided by dou t is equal to dou psi by dou s times us. This is a partial differential equation for the function of two variables psi t comma s with the initial condition psi of 0 comma s is s. So, we have proved the first part of theorem 5. Similarly, one can prove the second part of theorem 5. The proof of part 2. You start with the we start with the probability generating function psi of v plus h comma s is same as psi of v comma psi of h comma s. By Taylor's theorem, the right hand side becomes psi of v comma s plus h of u psi of v comma s plus order of h. Then take psi of v comma s in the left hand side, divide throughout by h, you will get this equation. Now, limit h tends to 0 plus and then substitute v is equal to t in this equation. Limit h tends to 0 plus and substitute v is equal to h, v is equal to t, we get a partial derivative of psi with respect to t is equal to u of psi of t comma s. This is the ordinary differential equation with the initial condition psi of 0 comma s equal to s. So, in the theorem 5, we conclude the probability generating function satisfies the partial differential equation and the initial and ordinary differential equation with the initial condition psi of 0 comma s equal to s. Now, we will find out the mean of z of t. You start with the partial differential equation satisfied by probability generating function. By differentiating with respect to s and interchanging the order of differentiation on the left hand side, we get the left hand side is the second order partial derivative of psi with respect to t and with respect to s. the right hand side u of s, second order partial derivative of psi with respect to s, u dash of s, partial derivative of psi with respect to s. If s equal to 1, you know that u of 1 will be 0. Suppose the m of t will be the mean of z of t, that is nothing but the partial derivative of psi with respect to s, then substitute s is equal to 1. Therefore, this equation becomes partial derivative of m of t with respect to t is equal to u dash of 1 m of t, since m is with the single variable. So, this is the ordinary differential equation. So, dmt by dt is equal to u dash of 1 times m of t, where m of t is a mean of z of t. But since z of 0 is equal to 1, m of 0 also 1. Therefore, you can solve this ordinary differential equation with the initial condition m of 0 is equal to 1. Hence, the solution will be m of t is equal to e power t times u dash of 1. Now, we can discuss the mean of z of t based on the value of u dash of 1. Before that, we discuss the probability of extinction, that is defined by q, that is nothing but limit t tends to infinity probability of 1 comma 0 of t. This is called a probability of extinction, that is denoted by the letter q. Now, we will try to find out the probability of extinction small q. Assume that a naught is strictly greater than 0, otherwise extinction is impossible. It is enough to consider the case where the process starts with a single individual at time 0. It means z of 0 is equal to 1. With s equal to 0, you will get a p I of 0 of t, that is nothing but a p 10 of t power I in the probability generating function of Pij of t. Now, we will prove that Pi0 of t is a non-decreasing in t. You start with Pi0 of t plus v, that is nothing but psi of t plus v comma 0 of power I, that is same as psi of t comma psi of v comma 0 power I, that will be greater than or equal to psi of 0 comma t power I, but that is same as Pi0 of t. Hence, we proved Pi0 of t is a non-decreasing in t. Let t be the fixed positive number. Consider a discrete time branching process z of 0, z of t naught, z of 2 times z naught and so on, z of n times t naught, where z of t is a population size at time t. Assume that the population size at time 0 is 1, z of 0 is equal to 1. Since z of t is assumed to be Markov process, the discrete process yn, y suffix n, that is nothing but z of n of t naught, will be a discrete time Markov chain, which is also a discrete time branching process, because z of t is a continuous time branching process. Therefore, y of n will form a discrete time branching process, which is also a discrete time Markov chain. By the hypothesis of homogeneity of a probability function of z of t, and the probability generating function of Pij of t, that is nothing but a probability generating function of Pij of t power P1 of 1 j of t power I. This we have proved it in the earlier. We have proved it in earlier. Therefore, using these two, we are finding summation over k, the conditional probability of yn plus 1 is equal to k given yn is equal to I multiplied by s power k. That is nothing but expectation of s power yn plus 1 given yn is equal to I. That is same as, because yn is nothing but z of n times t naught, therefore yn plus 1 is nothing but z of n plus 1 times t naught. So it replaces yn by z n times t naught and yn plus 1 by z of n plus 1 times t naught. This is true for all n, therefore that is same as expectation of s power z of t naught divided given z of 0 is equal to I. But that is nothing but psi of t naught comma s power I. But that can be written as expectation of s power z of t naught given z naught is equal to 1 whole power I. That is same as expectation of s power y1 given y naught is equal to 1 the whole power I. This shows that yn is a branching process. Yn is a discrete time branching process. So using this, we have proved the yn is a discrete time branching process. The probability generating function for the number of offspring of a single individual in this process is psi of t naught comma s. By theorem 3, we know that the probability of extinction for yn, that is a discrete time branching process, is the smallest non-negative root of the equation psi of t naught comma s equal to s. So by using the theorem 3, we conclude the probability of extinction for the yn process is the smallest non-negative root of the equation psi of z naught comma s equal to s. But we know that probability of yn is equal to 0 for some n, that is same as limit n tends to infinity of probability of yn is equal to 0, that is same as limit n tends to infinity of probability of z n times z naught is equal to 0, but that is same as limit t tends to infinity of probability zt is equal to 0. By definition, this is nothing but small q, that is the probability of extinction. Hence, the probability of extinction q of a continuous time branching process z of t is the smallest non-negative root of the equation psi of t naught comma s is equal to s. Here we have concluded by theorem 3 the probability of extinction for the discrete time branching process yn is the smallest non-negative root of the equation psi of t naught comma s equal to s. Because of this, we conclude the probability of extinction of the continuous time branching process z of t is the smallest non-negative root of the equation psi of t naught comma s equal to s, where t naught is any positive number. Hence, we expect that we should also be able to calculate q from an equation that does not depend on time. From this equation, can able to calculate q from the equation that does not depends on time. Now we are moving into Theorem 6, how to find the probability of extension. We conclude Q is the probability of extension for the continuous time branching process. So, here in this theorem we are giving the probability of extension Q is the smallest non-negative root of the equation U of S equal to 0. Hence, Q is equal to 1 if and only if Q dash is less than or equal to 0. So, whenever Q dash of 1 is less than or equal to 0, then the probability of extension will be sure, the probability will be 1. Extension event will be sure, the probability of extension will be 1. Now, we give the proof of probability of extension. In the earlier theorem, we have concluded Q satisfies psi of T naught comma S is equal to S. For any T naught greater than 0, we have this relation we have in the theorem 4. The theorem 4 discuss theorem 5 discuss the partial differential equation and the ordinary differential equation satisfied by psi of T comma S. So, we are using these equations to find the probability of extension. So, here by using theorem 5, psi of V plus H comma S minus psi of V comma S divided by H will be U of psi of V comma S plus order of H by H. You know that this will be tends to 0 as a H tends to 0. If S equal to Q, because Q is the probability of extension is the smallest non-negative root of the equation psi of T naught comma S equal to S. Therefore, if you substitute S is equal to Q here, then the above equation becomes the left hand side becomes 0. When you put S is equal to Q here, then the psi of V comma Q will be Q. Therefore, this will be U of Q plus order of H divided by H. By substituting S equal to Q in this above equation, the left hand side becomes 0. The right hand side first term psi of V comma Q will be Q. Therefore, it will be U of Q plus order of H divided by H. For any H greater than 0, it will be 0 is equal to U of Q plus order of H divided by H. As H tends to 0 plus, you will get a U of Q will be 0. Therefore, in the earlier theorem we have concluded the probability of extension will be psi of T naught comma S equal to 0. The Q will be the probability of extension is the smallest non-negative root of the equation. But here by using this we concluded U of Q is equal to 0. Hence, the probability of extension Q is the smallest non-negative root of the equation U of S is equal to 0 because we concluded U of Q is equal to 0. Suppose you find the double derivative of U, that will be greater than or equal to 0. Hence, we conclude U of S is a convex function in the interval 0, 1. As U of 1 equal to 0 and U of 0 is equal to A naught, which is greater than 0, US may have at most 1 0 in the interval 0, 1. The way we defined U of S, U of S is summation AK S power K. Therefore, U of 1 will be 0 and U naught will be A naught, which is greater than 0. With that assumption only, the probability of extension is possible. According to whether u double dash is less than or equal to 0 or greater than 0, we have the case q is equal to 0 or q is less than 1 respectively. That means when u dash is less than or equal to u dash of 1 is less than or equal to 0, the probability of extension will be 1. The u dash of 1 is greater than 0, then the probability of extension will be less than 1. So graphically one can show this is a graph of y is equal to u of s. So here we have two graphs. The graph A related to u dash of 1 is less than or equal to 0. Since u of s is a convex function in the interval 0 to 1 and u naught is a naught, u1 will be 0. So this is the graphical representation of y is equal to u of s when the case u dash of 1 is less than or equal to 0. The case 2, when u dash of 1 is greater than 0, the y is equal to u of s will cut the x-axis at some point which is less than 1, because u naught is a naught, u1 is equal to 0 and u of s is a convex function. U dash of 1 is greater than 0, the u of s will cut in the x-axis before 1. Hence, the probability of extension when u dash of 1 is less than or equal to 0, that will be 1, and the probability of extension when u dash of 1 is greater than 0, it will be less than 1. Note that expectation of z naught, expectation of z of t naught is equal to expectation of y if and only if u dash of 1 is strictly greater than 0. So whenever u dash of 1 is strictly greater than 0, the probability of extension is less than 1. This means that for a discrete time branching process z of n times t naught, extension occurs with the probability less than 1, and therefore the same is true for the process z of t. The probability of extension q is in the case necessarily the smallest 0 of u of s in 0 to 1. In a similar manner, we conclude that if u dash of 1 is less than or equal to 0, q must be equal to 1. In either case, q is the smallest non-negative root of u of s equal to 0. So hence, the probability of extension q is the smallest non-negative root of the equation u of s equal to 0 when q is equal to, when u dash of 1 is less than or equal to 0, the probability of extension will be 1. Now we will consider the limit theorem. If u dash of 1 is equal to 0 and u double dash of 1 is finite, then we can show this conditional probability will be approximately 2 divided by t times u double dash of t as a t tends to infinity. And also we can conclude the limit t tends to infinity probability of this event is e power minus lambda, where lambda is strictly greater than 0. When u dash of 1 is strictly greater than 0 and u double dash of 1 is a finite, then the z of t divided by e power t times u dash of 1 has a limit distribution as a t tends to infinity. Without proof, we are stating this limit theorem. Till now we have discussed two important branching processes. The first one is Galton-Watson discrete time branching process. The second one is a Markov branching process, which is a continuous type branching process. Now we are going to discuss some more or some other important branching processes. The first one is BellmanHarris processes. Consider a classical branching processes in which the progeny are born at the moment of parent's death. Let Zd be the number of particles alive at time t. The distribution of a particle lifetime tau is an arbitrary non-negative random variable. The resulting process is called the age dependent or BellmanHarris process. So, in the Markov branching process, the random variable tau, which is a exponential distribution, but here it is a arbitrary non-negative random variable, then the resulting process is a age dependent or BellmanHarris process. So, when tau becomes exponential distribution, then age dependent BellmanHarris process becomes Markov branching process. Assume that all particles reproduce and die independently of each other. The similar assumption we have taken care in the discrete type as well as continuous type branching processes. This model generalizes the birth-death process in two respects. The first, the lifespan of individual particles need not have the exponential distribution, and second, more than one particle can born. Because of these two aspects, this model generalizes the birth-death process. The process Z of t is not a Markov process, and its analysis is usually done by using renewal theory. We have discussed renewal processes in module 8. Now we discuss the BellmanHarris processes with a disaster. Consider the population model which follows a BellmanHarris process. At random times, disasters beset the population, and each particle alive at the time of disaster survives with the probability p. The survival of any particle is assumed independent of survival of any other particle. In this model, the measure of interest is limiting behavior when extinction does not occur. We will move into the other important branching process, that is BellmanHarris processes with immigration. In addition to the BellmanHarris process, we allow a sudden appearance into the system of newly born particles called immigrants. Immigrants are assumed to arrive in a group of various sizes with the probability of n immigrants in a group immigrating at time t given by Pn of t. Once these particles arrive, they reproduce and die according to the BellmanHarris process. In this model, measures of interest are the mean of Z of t, the limiting distribution, and the asymptotic behavior of Z of t. This process is widely used to describe growth and decay of biological populations. We are not discussing in detail of a BellmanHarris process in this lecture. In this module, we have discussed in detail two important branching processes, Galton-Watson process and Markov branching process. We have briefed BellmanHarris process with disaster and with immigration. In the first two branching processes, we have discussed the mean and variance of Z of t. limiting distribution, probability of extinction in both branching processes. Here are the references for this module 9 branching processes.